Hello students, now we are going to revise Foundation Advanced Lecture 8. In this lecture, we are going to discuss about Archimedes' principle. So the Archimedes' principle states that the upward buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid that the body displaces. Now we have already studied that the fluid displaced is equal to the volume of body which is inside the fluid. So basically when you see here, let's say the volume of this object is V. If the volume of this object is V and it is completely submerged in water, then the upward force, which is the buoyant force, let's call it FB, the upward force, buoyant force which is acting on it is equal to weight of displaced fluid which is equal to weight of the fluid which is in this jar. As the volume of this solid is V, the volume of this fluid which is displaced is also equal to V. The weight of this fluid is equal to mass of this fluid into G, correct? Now mass, as you know, is equal to volume into density. Now density of liquid, let's say, is rho. In that case, mass is equal to rho times V, and there is G here. So this is G. Now the buoyant force that is acting is equal to rho V G, correct? Where V is the volume of displaced fluid and G is acceleration due to gravity. Rho is the density of the fluid that is being displaced. Also, the direction of buoyant force is always upwards. Okay students, now let's move on to the next slide. In this slide, we are going to discuss about the apparent weight. You see here, this object weighs 5 kg in air. The reading on this scale is also 5 kg, correct? Now let's dip this inside water. When we dip this inside water, it displaces a fluid which is equal to 2 kg. So the buoyant force that will act on this block will be equal to 2 kg. And you also see that the reading of the scale now is 3 kg. This 3 kg is the apparent weight of this object. Now see here. Apparent weight is equal to the actual weight minus loss in weight, right? This loss in weight in liquid is equal to the buoyant force that is acting on the fluid. So basically the apparent weight is equal to true weight minus the buoyant force. Let's say this object has a volume V and the density of this solid is rho S and density of this liquid is rho. In this case, for true weight, this is equal to the mass of the object into G. Mass of the object is density of the object into volume of the object times G minus the buoyant force. Buoyant force is equal to weight of the displaced liquid. Now, weight of the displaced liquid, as we have seen earlier, is equal to rho V G, correct? So therefore, the apparent weight, or let's call it WAPP, which is the apparent weight, this is equal to rho S V G minus rho V G. So this is the apparent weight of the object. Now we have assumed that the object is completely immersed inside the liquid, and then we can apply this formula, correct? Now let's move on to the next slide. Next one, we have to solve this problem in which a iron block of mass 2 kg is submerged inside the water. We have to find out the buoyant force acting on the iron block and the force needed to hold the iron block still in water. So what is happening? We have iron block which is inside this container of water. So this is my iron block and this is completely inside the water. So the forces that is acting on this is buoyant force upwards, weight of the block which is acting downwards, which is mg, correct? So first of all, we have to find out the buoyant force. For finding out the buoyant force, we need the volume of the displaced fluid. As you know, the iron block is completely inside water. So volume of displaced fluid is equal to the volume of the iron block. For finding out the volume of iron block, I need density of iron. Okay, density of iron. Let's name it as rho. This is equal to 7860 kilogram per meter cube. Now let's find out the volume of this iron block. Volume, as you know, is equal to mass divided by density. So this is equal to mass, which is 2 kg, divided by density, and the volume is in meter cube, correct? Now let's find out the buoyant force acting. So the buoyant force Fb is equal to volume of displaced fluid into density of fluid into g, right? This is equal to weight of displaced fluid which is equal to mass, which is rho liquid, into V into G, correct? Now rho liquid, because this is water, the density is 1000 kilogram per meter cube into volume, which is equal to 2 divided by 7860 meter cube into G. The value of G is taken as 10. So the buoyant force is coming out as, after calculating, 1.27 Newton. So the buoyant force that is acting on the iron block is equal to 1.27 Newtons. Let's make the free body diagram. So upward force acting is Fb, and there is downward force acting which is equal to 2g, where 2 is the mass of the block. So I have to apply a force which is upwards, right, to hold this block still. Let's say this force is equal to T. Now for this block to stay still, the net force on the block must be equal to 0. So T plus Fb minus 2g, because 2g is acting in the downward direction, so we have a negative sign here, is equal to 0. So T plus Fb, which has a value of 1.27, minus 2g, which is 2 into 10, is equal to 0. And for solving, I get T is equal to 18.73 newtons. So the force that is needed to hold this block stationary is 18.73 newtons. Okay students, now let's move on to the next slide. Now we are going to discuss about relative density in this slide. Relative density is the ratio of density of the material to the density of water at 4 degrees Celsius. The density of water at 4 degrees Celsius, this is equal to 1000 kilogram per meter cube. So the relative density of a material is equal to the ratio of density of the material to the density of water at 4 degrees Celsius. Let's try to find out relative density for iron. As we have seen earlier, the density of iron is 7860 kilogram per meter cube. Now for the relative density of iron, the relative density of iron is equal to density of iron, which is 7860, divided by the density of water at 4 degrees Celsius, which is 1000 kilogram per meter cube. This is equal to 7.86. So the relative density of iron is 7.86. Now this is a unitless quantity. As it is a ratio of densities, it is a unitless quantity. Now let's move on to the last slide, which is based on law of flotation. An object is floating in any fluid because of the buoyant force which is acting on the object. Now let's say weight is acting on the object in the downward direction and the buoyant force is acting in the upward direction. If the buoyant force acting on the object is greater than or equal to the weight of the object, then the object will float. But if the weight of the object is larger than the buoyant force acting on the object, then it will sink. Now let's say we take a solid object. A solid object is the one which has no cavities. This is a solid object and it does not have any cavities inside. For this kind of object, if density of this object, which is rho solid, is greater than the density of the liquid it is placed inside, in this case the object will sink. Okay, if the density of the solid is greater than the density of liquid, the object will sink. But if the density of the solid is less than the density of the liquid, in this case the object will float. The example of this case when the object sink is placing an iron bar inside water, placing lead inside water, placing a brick inside water. All of these things have densities larger than water and they sink. Example for this behavior is when you place wood inside water. Because the density of wood is smaller than the density of water, it floats in the water. Also plastic floats in water because the density of plastic is less than density of the water. Now let's move on to the next question. In this one, there are two solids which are floating in the water. It is observed that A floats with half of its volume immersed in the water and B floats with 1/4 of its volume above the water surface. Now we have to find out the ratio of densities of A and that of B. Let's say the volume of object A is VA and density of object A is rho A. Now for this object, as it is floating in the water with half of its volume inside the water, that means it is displacing water equal to half of its volume. So as it is floating, the net force on this object is going to be equal to 0. So I can say that weight of the object A, which is equal to rho A times VA times G, mass into G, the weight of the object A, it is equal to weight of the displaced fluid. The density of displaced fluid, that is water, is rho W, into volume of displaced fluid. Volume of displaced fluid is half the volume of object A, which is VA by 2 into G. So from here, when I solve, I get that rho A is equal to rho water divided by 2, correct? This is going to be my equation number 1. Now let's solve for object number B. For object number B, let's say the density is rho B and the volume is VB. Now what we see is that 1/4 of the volume of object B is above water. So it is floating like this, and the volume of water which is inside the water is 3/4 of the volume, or this is equal to 3/4 of VB, correct? Now as the object is floating, the bind force acting on the object is equal to the weight of the object. The weight of the object is equal to rho B VB times G, which is mass of object B into G, which is equal to the bind force, which is equal to rho water into the volume of the displaced fluid, which is 3 VB by 4 times G, correct? Now when we solve this, we get rho B is equal to 3 rho W by 4. Let's name this equation as equation number 2. Now we have to find out the ratio of density of A with that of B. Therefore, I have to find out rho A by rho B. Now from equation 1 and 2, I see that rho A is equal to rho W by 2 and rho B is equal to 3 rho W by 4. So when I solve this, I get that this is equal to 4 by 6, or this is equal to 2 by 3. So this is my answer, that the ratio of densities of A to B is equal to 2 by 3. Thank you students. That is all for this video.